Good morning, good afternoon, and good evening to everyone. I'd like to, first of all, thank Gerald for facilitating this webinar, and of course, Park AFM for sponsoring the webinar meeting. I'd like to begin by also thanking the audience for you taking out of your busy schedule to attend this webinar. And for those of you who are in the Eastern time zone in the US, you're probably having your lunch in front of your screen. So bon appetit. I would like to begin by stating my affiliation. I'm a professor at Case Western Reserve University, Case School of Engineering. And also, as the title says, I'm the director of Petro Case, which I'll have an opportunity to expound to you in a little while. And of course, if you have any questions, you can email me at rca@case.edu even after the seminar. And you can also get the help from Gerald as well as post questions on the chat mode of your webinar. So first of all, Case Western Reserve University, we are located in sunny Cleveland, Ohio. Yes, it is sunny here right now. That's one of the rare days. We love this area. My family and I moved here 3 years ago. Case is located at the University Circle, home of the Cleveland Orchestra, Cleveland Museum of Art, and of course the Case Western Reserve University, which is shown in this picture. Case has a long history dating back in 1826. In fact, one of the founders of, the founder of Dow Chemical is a graduate of Case Western Reserve University, Henry Dow. Recently, we started a additive manufacturing ideation innovationeering center called ThinkBox, and this allows students, professors, researchers, collaborators to tinker and creatively invent with tools like 3D printing, laser cutting, and basically allowing us to have both students and researchers engage in new ideas and fabrication. Our home is with the Case School of Engineering, Department of Molecular Science Engineering. Shown here is a slightly older picture of my research group. We are located at the 5th floor of the Kent Hale Smith building. Of course, being a professor, it's a publish or perish mode. In our lab, we have been doing a lot of research for since 20 years now on areas of patterning, interfaces, colloidal chemistry, thin films, coatings, and other types of nanostructured and nanomaterial-based synthesis, as well as ordering. On the other hand, our group is very much involved also with industry. Here are shown some of the companies we work with, either both on individual projects, long-term projects, some of which involve consulting, and you can see the variety of industries that we work with, ranging from coatings to formulations, chemical companies, oil gas services, as well as other energy companies. Last year we started Petro Case. This is a center, a consortium that focuses on materials needs for the oil and gas industry. We are focusing on high performance materials, coatings, fluids, different types of tools, materials, modular tools for productivity. For example, focusing on the unconventional oil and gas, which means these are technologies and materials that can perform under extreme conditions or high pressure, high temperature, brine conditions, etc. On the other hand, a very important aspect of this industry is the parity between cost and productivity or yield of production. And that means having the right tools, materials, inhibitors, additives that can result in high yields of oil and gas over time, and at the same time maintaining or lowering the cost of production. Lastly, preserving assets, whether it be a platform offshore, onshore, and its environmental impact, or involving the use of bio-based materials, sustainability is also part of our goal. That means that in the area of polymers, one can go from thermosets to elastomers to different types of additives that goes into the produced oil or water or gas. This also involves investigating the optimization of colloids and surfactants for emulsification, demulsification, different types of corrosion and scaling additives, as well as for enhanced oil recovery. Another aspect is that we're interested in new processing methods such as 3D printing to improve the performance and rapid prototyping, as well as facing the challenges of manufacturing tools, in particular non-metallics or polymer-based components to the industry. Okay, so a little view here of our laboratory. We are located at the 5th floor of the Kent Hale Smith building, very well equipped both in chemistry, analysis of materials, rheology, different types of tools for investigating coatings, including several atomic force microscopy, vibrational spectroscopy, and more recently we have been developing a lot of tools for stress testing, environmental testing, core flooding, permeability measurements, flow chemistry, and lots of tools for Proppant testing. In fact, even back in 2009, we have been very much involved with the synthesis and characterization of resin-coated sands or Proppants used in hydraulic fracturing. Of course, we also have access to other instruments at Case Western Reserve University. In particular, we have excellent tools for mechanical testing, thermomechanical testing, corrosion, imaging, different types of compression tests, reliability of devices, and so on. I'd be happy to share some of what we have. So we're fairly comprehensive in the School of Engineering in access to things that we need at the center and beyond. Okay, so let's get some definitions first. Innovation, why is it a key word in what we do, whether it's industry or even in academia? Well, we are in one way interested in having people invest, buy our products, or simply look our way in terms of what we do. And defining innovation that means differentiating it from invention. Invention is, of course, producing something that can solve a problem or even patenting an idea. On the other hand, going beyond invention means that somebody is willing to pay for it. And that's where invention is differentiated from innovation. Innovation is a stage by which your idea or invention is very useful and important to somebody or another company that you're willing to pay for it. So much of what we do, for example, in the university is, of course, basic research, and the primary product of our work is not actually the research output or the publication or the IP, but what I consider as a main product are the people who get their degree in our university, or specifically my group. On the other hand, the industry is always involved with the market, trying to satisfy the market or the commercial viability of their products. So how do we bridge with what comes from the university all the way to the industry? It's called translational research or applied research. That means that we take the best basic science platform that can come from the university, innovate it, optimize it, fabricate it in such a way that it becomes an exact solution or device that meets a market need. So in a way, innovationeering is solving problems optimizing, increasing efficiency, or basically improving the cost-performance ratio of a product that may have come from the university. Okay, so oil and gas production and distribution. Let us have a quick review of this value chain. So primary, secondary, tertiary refers to how easy it is to extract oil. In a sense, primary is a majority of oil that was gathered more than 150 years ago, in that they were easy oil. But a lot of oil that are found, especially in North America, ranges from secondary to tertiary. In fact, only the Middle East or certain parts of the world is it easy to focus on what we call conventional oil. But largely, what has been important focus is on extracting heavy oil, oil sands bitumen, or even shale oil and gas, which has been accessed by hydraulic fracturing and the use of directional drilling. So the demands are very challenging, especially as you go to deeper formation, higher pressures, high brine conditions. Midstream means efficient transport and preventing any blockage or keeping the flow assurance. And downstream, of course, refers to the refining industry. So there are demands on both directions, from upstream to downstream, but we are specifically looking at the chemistry and materials needs of the oil field, that is upstream, unconventional resources, and for example, shale oil and gas or hydraulic fracturing. So here is our summary of the challenges that we are facing. High-performance polymers and additives. There's high interest on unconventional resources, enhanced oil recovery, and of course, well stimulation. As you go offshore to depths of about 20,000 feet, pressures about 10 to 15,000 psi, very high salinity, HPHT conditions, a lot of materials cannot do the job properly and need replacement. On the other hand, a perennial interest is in keeping the yield or increasing the yield and lowering the cost for production. Here, for example, we are also focusing on corrosion, fouling, flow assurance, problems with sweet and sour corrosion, and brine. So these are perennial production problems that has been the focus for many types of companies in providing solutions, either as coatings, additives, inhibitors, or different models of predicting problems. Water resource is very important in hydraulic fracturing. Most of the procedure out there involves a lot of gallons, millions of gallons of water. In fact, in many areas that require transport of water, that easily comes as the main parameter or cost for fracturing economy. So there's a need for waterless fracturing technologies, for example, to replace them. There's a need for sustainable practices, use of renewable resources, which can save costs and maintenance, but at the same time, there's, of course, the need to keep it at parity with performance. Lastly, there's a need for new testing facilities, materials characterization, and even experimental field and stimulation wells to test a lot of the chemistry and materials needs. So take, for example, hydraulic fracturing, which is largely done on shore. These projects range from several millions to tens of millions of dollars. What this means is that as you go to, let's say, 10,000 feet below the surface, you need to pressurize this formation, which is very low darcies or nanodarcies in permeability. with shale formation simply by using or pumping highly pressurized fluids or frac fluids, which are viscosified. This results in formation of cracks or fractures or fissures that needs to be kept open. So, for example, a key material additive here is the use of proppants or propping agents, which can be in the form of sand, ceramic, or resin-coated sands. And as you can see in this illustration, the job here is to keep those fractures open such that you will have production yields well beyond after the initial year of the production phase. On the other hand, a perennial need is, of course, things used for subsea engineering in platforms, as well as different types of needs for LNG storage, as well as refining. You can see here that both depth, salinity, cryogenic service, different types of exposure to the environment are very important. Corrosion, it's a problem not only for the oil and gas industry, but many structural, automotive, and other costs in our society, which is actually about 5% easily of any country's GDP. And that means that you need to focus on coatings, in human lives, but environmental disaster, as well as a black mark in the industry. So a lot of materials needs to simply prevent failure is a very important goal in the oil and gas industry. Okay, so let's start heading towards materials, polymer materials. So I'm showing this chart just to show you that when we talk about polymers structuring, we are not dealing with only linear polymers, but we are dealing with networks, branch, dendritic, different types of cross-linked systems. In fact, elastomers, rubber, etc. are differentiated from thermoplastics, thermoplastic elastomers by their degree of cross-linking. Or gels that are viscosified can have non-covalent cross-linking as well. There's a lot of interest in dealing with what we call hyperbranch or dendritic systems. And polymer architecture also means you need to account composition, molecular weight, and so on. I'm a polymer chemist, so I love showing this plot because a lot of things that we're going to talk about today deals with polymers as well. Now, polymers, on the other hand, take advantage of what nanomaterials and non-interfacial science has to offer. Maybe it's in the form of composites, additives, different types of sensing agents, etc. You can see here the different problems where polymers can be a solution in midstream, upstream to downstream. Perhaps a better pictorial representation is this. Here you can see drilling fluids, diverters, viscosity modifiers, proppants, cements, dispersant, pipes, blowout preventer, packers, etc. makes use of polymers. In fact, the oil and gas industry loves to use the word non-metallic, and whenever I have a chance, I usually just correct and say it. You are actually referring to polymers, right? Well, of course, non-metallics can also refer to ceramics and non-metal analogs, but largely non-metallics in the oil and gas industry refer to thermosets, thermoplastic elastomers, thermoplastic pipes, etc. And these are, of course, polymers. And here you can see pictorially where some of the polymer materials can be in the form of sealants, completion tools, blowout preventers, different types of packers, different parts of the oil rig, etc. Now, what we are referring to are basically the hierarchy of polymer materials starting from base or commodity polymers. So whenever you encounter polyethylene, polypropylene, PVC, polystyrene, these are high commodity polymers used in everyday things. On the other hand, the tip of this pyramid are what we call ultra polymers that are very hard to process, yet are the most high performance enduring polymers that is actually used by the industry, ranging from PEEK to PEAK, PBI, PPS, and these are also expensive polymers to use. Elastomers, FKM, FKM, etc. Fluorinated systems. These polymer materials are being used increasingly to replace metallic parts, and also rubber, HNBR, NDR. These are very commonly found in blowout preventers, packers, hoses. Are used for the longest time, but actually needs updating. So there are many choices. The question is, when do you start introducing these high-performance materials more commonly, and reducing in price and improving their performance? So the next slide shows what we have been trying to do and what is of interest to other groups as well, is to bring in, let's say, 3D printing or additive manufacturing to the oil and gas industry. Some of the candidates could be PVDF, PEEK, PBI, FKM, PPS. These are difficult to process extruded materials, not easily polymerized as well. In fact, the problem with 3D printing is weakness in one axis of the direction of the material, that is a layering process by FDM. This needs to be solved, but there's a lot of potential because, as the next graph shows, 3D printing or different types of additive manufacturing process is very much in tune for materials needs which require high performance, complexity of design, lower volume, which is basically space we're looking here. On the other hand, where you need high volume, high throughput output, different types of molding, extrusion methods are basically confined in this phase, but they are not capable of a complex design. So increasingly, there should be a lot of interest, let's say, in bringing additive manufacturing to the oil and gas industry. And we are in the process and at the forefront of developing new materials and processes for that. So going back to the original theme and title of the meeting, why nanomaterials? Why the interest in different types of nanostructuring? As you can see here, dimensionality of nanomaterials range from several nanometers to hundreds of nanometers, whether we're dealing with carbon nanotubes, graphene flakes, different types of nanoclays, colloidal particles or quantum dot particles. Increasingly, these have found ways in improving nanocomposites as well as formulations of paint, different types of viscosifiers, different types of composites that can even have some sensory function. On the other hand, here you can see that the polymer itself, a single polymer chain can have a hydrodynamic volume depending on the solvent as either a swollen or contracted phase, which can be complex or part of a colloidal dispersion, a Pickering emulsion. That means that a polymer has a very important role in formulation process or fluids, hence fluids. On the other hand, the other part here shows that a polymer can be ordered or structured at interfaces, different types of compositions that can go into membranes, films, barrier materials, and so on. Here, I'm just showing that as a group, we have been very much involved in the synthesis of new polymers. A lot of these polymers, in fact, have found its way in smart coatings, different types of devices. We are very much in tune with the advances of synthetic chemistry, and so is with the chemical industry. So part of the things that we do for industry and in the consortium is basically to bring the best chemistry coming from the chemical companies, coatings industry, to the toughest problems of the oil and gas industry that requires innovation. For example, we are pioneers in the area of polymer grafting or polymer brushes. We are capable of modifying surfaces, whether it's metallic surfaces, rubber materials, thermoplastics, with grafted polymer systems. Now what they do is they enhance compatibilization in composites, or they enable modification of surfaces or coatings so that they can have super hydrophobic nanostructures as well as different types of chemical and physical integrity over long periods of time. Another is that what you can do on a flat surface, you can translate them on particle surfaces. For example, we have a long experience in modifying clays, silica particles called nanoparticles, and we have used this to our advantage to modify formulations and compositions. For example, a lot of work we've done is based on modifying clay particles, nanoparticles, either montmorillonite, bentonite, hectorite, laponite clays. Of course, the oil and gas industry is very familiar with bentonite, different types of clays that are used for modifying the viscosity of drilling fluids, different types of additives for completion fluids, as well as midstream applications. So we have a lot of experience in modifying these polymers for a number of those applications, and also for improving composites. Here, again, just showing you some of our synthetic prowess. We can work on modifying nanoparticles with different types of dyes, branch systems. We are interested, for example, in using this type of nanomaterials as sensors and markers for different types of tracers that can be used in the oil field, from the exploration phase to monitoring different types of enhanced oil recovery pathways. We have prepared smart surfaces by templating. An example is how we have used colloidal particles, which the coatings industry know as binders, made up of emulsion polymerized polymers. Here we have two-dimensionally patterned them on surfaces, and we were able to electropolymerize around it such that we can preserve and obtain honeycomb structures. Now, these are very interesting structures in that we can do dual chemistry as well as smart surfaces for sensing molecular printing. I'm not going to talk about that today, except that in the course of our work, we have discovered that, again, here you can see the fidelity of the pattern we can prepare. Basically, what happens is we have these colloidal templates. After polymerizing and removing the colloids, we end up with honeycomb structures like this. So in the course of our work, we accidentally polymerized too much material on top of this surface. And here you can see still the colloidal particles and the roughness that we achieve. By techniques like IR imaging, we were able to confirm the presence of the polystyrene particles and the polymer material we electropolymerize on top of it. Now, it's interesting in that with this, actually, we discovered that this type of coatings have very good properties of what we call a super hydrophobic effect. The super hydrophobic effect means it hates water or is self-cleaning. And we achieved this on this polymer material, polythiophene, that was polymerized on top of those colloidal particles. On the other hand, we found that these coatings actually are super lithophilic, meaning they love oil. So, gee, what can we use these materials for the oil and gas industry? Well, it hates water, it loves oil. So it must be a very good oil and water separator. In fact, it is. And we have developed some experiments, and I'll show you in a little while. So for example, oil water separators, whether it's onshore, offshore, is very important because of environmental regulations that control the amount of water contaminants in water before discharging it as waste or processing it. On the other hand, accumulating as much of the produced oil for production, or even controlling or mitigating the effects of oil spill. So some of these materials have found their way there, and I'll be happy to expound it in offline to some of you if you have any questions. These are also smart surfaces. In fact, as you can see here, the hydrophobic, super hydrophobic material form is orange in color. On the other hand, the hydrophilic form of the coating is green in color, and they are switchable by voltage, so from 0 volt to 1 volt with a constant potential application. What it is it's taking advantage of what we call the electrochromic and electrowetting effect of conducting polymers, essentially in a oxidized form. It is wetting. On the other hand, in its reduced form, it is non-wetting and therefore super hydrophobic. These are also coatings that have very high anti-corrosion properties, close to 99% even after 2 weeks of exposure. Salt spray test, environmental test. They are super hydrophobic, and also the hierarchy of the roughness. Basically, what we're taking advantage here of what they call the Cassie-Baxter effect in wetting, which is a modification of the Young's equation. That means that you have inability to form continuous line tension of wetting, and at the same time, the void spaces and this coating results in trapped air. And the interest here is, of course, well, how can you use these coatings? How can you keep these coatings? And how can you prevent any abrasion from affecting their performance over long periods of time? We have recent advances on this based on different types of nanocomposites that can be coated on steel, prepared as aerogel, formulations. For example, some coatings would mimic the structure of a lotus leaf with a reversible wetting behavior based on temperature. That means they're stimuli responsive. I cannot reveal you the exact composition of this coating simply because they're under patent disclosure, but we've been able to achieve coatings that are stable even up to 400 degrees Celsius. So that gives you a clue that we can work on thermosets. On the other hand, with a variety of composition, we can make them thermoplastic or even elastomeric by the incorporation of elastomeric components. So again, I cannot reveal much of this except that this has becoming our workhorse on the current research. Just to show you some of the properties, when we prepare this as coatings, these are super hydrophobic coatings. The definition of a super hydrophobic contact angle is a value beyond 150. So clearly here, at different pHs, they are super hydrophobic from acidic to alkaline, but also they're superior coatings in terms of adhesion. So by doing, let's say, this ASTM D3359 test, very little material is removed on this materials, and they have very good adhesion. And right now, we're interested in some of their abrasion properties. Here you can see their morphology even after immersion by optical microscopy and SEM. There's no corrodants, or very little corrodants that adhered to the surface of the coating even after 7 days. What we believe is happening here is the composition we have follows a tortuous path of the diffusion and migration of corrodant species such as oxygen or water. Both the TAFL plots and the EIS measurements reveal that we can achieve very high efficiencies, up to 99 to 95% for different compositions. Therefore, what it means is that you have very good coating integrity and lack of transport of corrodant species. On the other side, which is, by the way, the typical solution for corrosion, are basically hermetically sealing the other side of the carbon steel, let's say, from the corrodant environment, whether it's sweet or sour corrosion, biogenic, abiogenic, H2S, or simply a water from produced water and brine. Now let me go and switch to another direction. Here, what you can see are pictures not only of corrosion but also blockages or flow assurance that results in deposition of scale or asphalt or paraffin. These are perennial problems of the oil and gas industry, especially the transport of oil and gas, or simply taking care of the health of your casings or field, the drilled field. That is, over time, scaling can occur, which comes from sulfates, magnesium, calcium, different types of phosphonates. Paraffin can be in the form, of course, of deposition of waxes or asphaltene, which are some of the natural surfactants present in oil, which are, so both paraffin and asphaltene is a huge problem, which can result from low pressures, low pressures, low temperature, flow conditions. And this is usually mitigated by the addition of chemical additives. So chemical additives is a very important aspect of the industry. Sometimes it's a very big component of your cost of maintenance. A lot of it, of course, is fluid control. So fluid control, whether at the initial phase of drilling, completion, or production, means you're dealing with viscosity, pressure, different types of lubricity, pumping rates, high pressure, whether you're dealing with emulsion, suspension, or solution. So by the way, of course, oil is an emulsion, water in oil emulsion. On the other hand, over time, when you produce more water, it becomes an oil and water emulsion. Erosion, corrosion caused by suspension or different types of particles that is part of the produced oil. It's a big problem not only in the oil and gas industry, but in fact with the geothermal industry. And I've worked with the several geothermal companies over the years. They have different sets of problems, but nevertheless, it's all about fluid control and flow assurance. So where does polymers and colloidal phenomena again play into? Polymers are used as inhibitors for scaling and corrosion. Different types of polymers can be used for enhancing viscosity. So think about guar, xanthan gum, polyacrylamide, different types of colloids as well. Polymers or oligomers can be used as defoamers, demulsifiers, or even emulsifiers, the other way around. And they are, of course, a composition of smart coatings as shown here. So polymers are an integral part of what we call smart materials, or stimuli-responsive materials that could be of high use to the oil and gas industry. So here I'm showing to you the different types of smart design, whether it be black copolymer, micelle surfactants that are able to capture paraffins, or different types of nanogel behavior that are stimuli responsive, are sort of on and off viscosity modifier, or different types of coarse shell systems that can produce Janus particles separating oil and water, hence, for example, producing Pickering emulsions, or different type of coarse shell particles that have different aggregation and swelling and contraction behavior with similar response. Another is there's a lot of interest also on degradable, even biodegradable materials. And being the oil and gas industry, of course, price sensitivity is a must. So here I'm just showing you some of the typical chemical components that can be used as inhibitors, scaling control, or even asphaltene control. In fact, you may be surprised that what I'm showing you is basically 30-year-old chemistry. That is, in the 70s, when the price of oil was very good during the embargo, lots of money was used, or investment was used in research. But in the 80s, even 90s, price of oil went down. So not too much innovation was channeled in the chemistry of the oil field or production. So in fact, what's happening now is a lot of chemical companies are interested in bringing new chemistry to the marketplace or meeting the demands and needs of the oil and gas industry, and hence there's a lot of chemical innovation that can be done. So let's proceed. For example, here I'm showing typical corrosion inhibitors that can come from imidazole-based chemistries that form films, let's say on a carbon steel. This can be as simple as fatty acids or lactinic acids or different types of chelating and electron shuttle modifications as inhibitors of part of the coating or the component itself of the fluid. Scaling inhibitors are basically inhibitors, ligands, polyelectrolytes, polymers that can control aggregation, preventing the deposition from supersaturated high-brine fluids or preventing their formation as aggregates or clusters in the first place. A lot of this has to do with ion control. Asphaltene dispersants and inhibitors can be found in terms of controlling the deposition of asphaltene, as shown in this box figure, which can be done by using resins, polymers, or different surfactant-like behavior where the pi intercalation or interaction with the asphaltene allows it to be removed, deposited, or kept in emulsion for a long time. Here is the structure of a polysaccharide that can be found in the drilling fluid. So we're referring to guar or santangam or even starch or other types of polysaccharides that can be used to modify viscosity. Another important polymer, which is also used for enhanced oil recovery, could be in the form of polyacrylamides, different types of vinylic polymers, but in general, these are commodity items that have been used for a long, long time. I'm not going to talk much about enhanced oil recovery for lack of time as well, but here you can see that chemical flooding, polymer flooding, or use of surfactants and foam is one option compared to the use of steam or different types of gas enhanced oil recovery methods in the industry. So enhanced oil recovery is basically increasing the production of a low-performing field by using tools, whether it's polymers or gases or different types of flooding schemes, driving it towards the production well. So cleaning up different conformal stability as well as viscosity to drive essentially the hard-to-reach or oil in the first place towards constant flow towards the production well. And this is a long-term research, and it sometimes suffers in terms of direction, investment space, especially with the low price environment of oil today. But yet a very important aspect of the industry. So again, what do we have to offer? Well, we know a lot of systems for synthesizing smart polymers, different types of vinylic, styrenic, and acrylic types of derivatives. So just showing that there are options other than free radical polymerization of polyacrylamides that allow one to produce different type of branch smart polymer systems. In fact, we are very interested in what we call hyperbranch polymer systems. So these are again in the scale of nanometers when you take the hydrodynamic volume into account. These are hyperbranch systems that tend to control or give low viscosity systems. On the other hand, high molecular weight random brush copolymers or gradient brush copolymer systems are very interesting in terms of their stimuli response. For example, we played around with RAF polymerized polyacrylic acid and polyacrylamide copolymers. We've been able to tune their viscosity based on their composition as well as the structure of incorporating hydrophobes that are more oil friendly versus the hydrophilic backbone. So a lot of play here can be done, a lot of interest, for example, even controlling the properties of asphaltene. Here, for example, we show a modified asphaltene particle with a polymer shell that we observed by TEM. And I'm not able to give further explanation on this, again, because of some of our patent disclosure guidelines. Here, for example, control of emulsions, very stable emulsions of fluids, drilling fluids, phase-separated systems, controlling their wicking behavior, or even their buckling phenomena at the oil and water interface. So we are very much involved in very stable as well as very unstable colloids, depending on the polymer surfactant that we use. Cements also is ripe for innovation. Polymeric additives in cement can be used to enhance their curing or sharpen their curing temperature and conditions, as well as modifying the surfaces of cement to make them super hydrophobic, for example. So going back to hydraulic fracturing, fracturing fluid essentially is 99% water, 10% to 1% the Proppant. Essentially, fracturing means that you are able to keep the health of the casing or the drill project, maintaining the integrity of flow assurance, lubricity of high pumping rates, and at the same time introduction of proppants that can be used to keep the fractures open and allow the gas and condensates to flow towards production. Now, frac fluids, there's a lot of talk on it about its environmental risk, but in general, the hydraulic fracturing, there's more concern actually on what's taken out of the ground than what's injected on the field. So focusing now on proppants. In fact, we have worked a lot on proppants for the last 5 years. We've worked a lot on what we call resins or polymeric materials. A typical proppant is basically well-rounded sand, and high-quality sand is used for most projects. The problem is that sand can produce fines. And in fact, I'm a proponent of using smart proppants for completion, simply because over time some of these sand frac projects have lower yields. And I believe this has to do with some of the problems in matching the specific gravity and the compressive strength of the proppant material. In fact, the best high-strength materials are basically ceramics. The problem is they're quite expensive. So a medium-strength, irregular size shape, resin-coated sand is an option. You are using basically anywhere from 200 to 400 tons of this proppant for drilling hole project, and that means you use lots of them to improve the production yield of those different fields over time. Now, the chemistry there for resins are basically based on cross-linked thermosets, although there's a lot of interest and we are working on thermoplastics. Most of these are dominated by Novolac type of resins or phenol formaldehyde. Some of them are based on polyurethanes or epoxies. And they are used to, again, improve not only the preventing the formation of fines, which is basically crushed sand, but also to improve the chances for packing, as well as preventing embedment and the formation. Or some of the things that we're concerned is in terms of the wetting behavior when you switch to the production phase. So in this case, there's lots of chemistry and lots of things to improve on proppants, which is, again, a very important component in shale oil and gas or hydraulic fracturing, a very important aspect of the industry, both the supply chain and the oil field service companies as well. Now, I'm almost done. What I'm trying to point in this slide is that as much as we like to see oil and gas being in the realm of operators or oilfield services, it's actually is a chemical industry, a 20 billion chemical industry, ranging from drilling fluids to cementing additives to stimulation chemicals or inhibitors, and as I've shown you last, polymer or resins that are used for coating proppants. There's a lot of interest for chemical companies to vet their products or best chemistries to the toughest problems of the oil and gas industry. It is indeed ripe for innovation. There's a lot of things to do. We've been very busy. The consortium I have works for both with both operators and oilfield services. On the other hand, we work with a number of chemical companies to test their products and improve their chemistry or chances for adaptation. Recently, we've written several review articles. Some of them have been published on their way to publication. Be happy to share them with you as soon as they become available. So with that, I'd like to thank you. Be happy to spend some time now answering your questions. And this is a list, for example, of things that we do in our lab and services that we provide. So with that, thank you, and be happy to answer any questions. So that's it.
Very good. Thank you very much, Professor. So, as our speaker just said, if you're not already familiar with the rules of the session, go ahead and enter your questions through the chat or the questions module in the control panel that loaded during the session. I'll go ahead and read them out loud, and then the professor can give his thoughts on your question. All right, so it looks like a couple have been put in here. So our first question here is, could you give an example, Professor, of a waterless fracking solvent?
Okay, so a waterless fracking, if we are referring to fluids, of course, there are fluids based on naphtha, diesel, even certain emulsions. They have been tried. Some of them have been effective. In fact, in formations where you have swelling of the shale or clay, you have to avoid water-based fluids as much as you can. So those have been tried. Other types of fracking procedures are emerging based on nitrogen gas, CO2, supercritical CO2. So these options are being explored in terms of their cost performance or even supply chain as an alternative to hydraulic fracturing. I cannot name some specific companies, Calfrac, Gasfrac, although I think one of them might have actually went bankrupt. Lind has a lot of interest in using gases for fracturing and so on.
All right, thank you very much. So I have been getting a couple series of questions here regarding the recording of the webinar and its availability. So just to address that, yes, the webinar has been recorded, and our ultimate aim is to eventually upload it for dissemination either through parkafm.com or through another website that we may launch in the future. Eventually, we will be making these available. I don't have a clear timeline just yet on its availability, but rest assured this material that was recorded today will eventually be made public for public viewing. Another question that I have been receiving from a number of our guests today, Professor, is they're interested in looking at your slides after the session. As far as I know, we won't be distributing them through Park Systems' channels. Are your slides going to be available upon request if our guests email you, Professor?
Yes, we'd be happy to respond by email for the slides itself. And I have a version that can be sent out. So yes, please just email me directly. I'd be happy to respond with you regarding the sharing the slides.
Fantastic. So I guess to help help that process along, Professor, could you show your title slide again for the presentation with your email address on it?
Okay,
Okay, very good. Thank you. All right, we have another question from the audience. There's the slide there, and as you can see, there's the professor's email address at the bottom of the slide. Our next question says, what is the capability of your lab, professor, in doing catalytic hydrochemical processing for, let's say, converting non-conventional biomass feedstock like algae?
So unfortunately, we don't have that capability, although I can probably by communication refer you to some labs outside of CASE. I believe no one at CASE is doing that type of research at the moment, but I do know some colleagues outside of CASE who are doing that, and I'd be happy to refer them to you or to the correspondence.
Very good. Okay, so I guess we'll wait a couple more moments for any questions to come in. It looks like we've exhausted everything that's been sent in so far. So once again, my name is Gerald. I'm from Park Systems, and this was Professor Rigoberto Advincula of Case Western Reserve University. If you have any questions that you think of after today's session, maybe during your lunch hour or so, or later in the day, as you can see, there is the professor's email address. I myself can be reached at gerald@parkafm.com, and I'll be sending that in the main chat to everyone in the audience if you have any questions about Park Systems itself. So let me go ahead and send that out. All right, and it looks like we have another question that came in. Question reads, Professor, do you do any characterization on natural bentonites that you use for your polymer modification based on the sources that you have? And as a follow-up, what type of natural bentonites do you use?
Okay, so yes, the tools we use are as follows. We use X-ray diffraction to characterize periodicity. Of course, we use also imaging tools like SEM and TEM on properly contrasted clays. We use thermogravimetric analysis just to distinguish the organic and inorganic component. On the other hand, we are also interested in using different types of indentation tools, even non-indentation tools. And AFM, for example, is a key tool when we're dealing with exfoliated clays. In terms of their property as a rheology modifier, we would have a corresponding model fluid, even drilling fluid, that we can use the bentonite clay and characterize their G prime, G double prime, not only viscometry, but different types of rheological parameters, oscillating and dynamic measurements. And we can do that. Now, as far as the grafting of the clay, we've done things with montmorillonite clay. Now, sources of clay, most of it are based on additives, and we use some clays coming from Baroids or Halliburton as well, but we typically work on different types of clays as well, beyond bentonite. So most of the things we try to do in modifying bentonite is investigate cation exchange, organocation exchange to modify their surfaces, as well as dispersing them using exfoliation methods such as sonication, just to investigate how we can break this into smaller pieces and modify them.
All right, so we have a couple more questions here. Our next question is, what are the unmet needs in Proppant coating?
Okay, so very interesting question. Well, the idea of Proppant will be a low specific gravity and high compressive strength or crash strength. That has to do with the Proppant that has to be introduced to the fracture via a carrier, which is your frac fluid. So it has to match the viscosity as well as the specific gravity of the fluid carrier. Once it gets into the fracture, then it has to withstand the crushing strength of, let's say, 10 to 20,000 psi, and that means it has to have very high crush strength or compressibility. So those are the two basic needs, and most of the Proppant companies, of course, are interested with those costs. Now, the other unmet needs are as follows. One is, of course, preventing fines if you're dealing mostly with sand, and therefore you need to produce very good resin coatings, whether it's a thermoset. In our case, we're interested in both thermoset and thermoplastic materials. Other is being able to switch it to a surface wetting condition that allows oil to wet it. So, for example, one of the things we're interested is in switchable coatings that go from hydrophilic to hydrophobic once it's exposed to oil. Another is being able to resist different brine conditions or even CO2 conditions that can degrade the coating itself. Another issue is with most phenol formaldehyde type of resin material is, of course, the effect of acidity in that you end up producing phenols and different types of what environmental with environmental concerns, but that's more of a minor issues. There's also interest, for example, in sustainable resin ingredients that is derived, let's say, from more biodegradable or bio-friendly type of components.
Okay, very good. All right, Professor, just as a time check, we've reached the top of the hour, and we have, let's see, 2 questions in the pipeline here. Do you want to go ahead and just answer them quickly here for the audience?
Yeah, short, quick answers to keep it on time.
No problem. The next question reads, where do you see the direction of power sources moving in the near and distant future? Is oil and gas sticking around?
Oil and gas will be around. It will be around for a long time. Basically, most of our energy needs and economy is an oil and gas economy. To go to renewable, non-oil and gas type of sources, our alternatives are basically nuclear, solar, wind, hydroelectric. Those are considered, of course, environmentally from the standpoint of not consuming fossil fuels, but in general, there's a fundamental chemical advantage of any oil and gas energy source. That is, they are directly converted into heat or energy that is very useful, whereas there's no need for storage of them, unlike, let's say, electrical energy that is derived from solar or wind. They have to be stored and distributed. So as an energy source, let's say for automotive or even gas generators, fossil fuels have an inherent advantage and of course, cost. And they will be here for a long, long time.
Well put. Okay, and the last question that we'll be taking today reads, do you think there is a polymeric lining for geothermal pipes and equipment that can survive at high temperature and brine conditions and simultaneously prevent silica scaling?
We're working on that. So we are working on that. That is, in fact, the challenge that we'd like to face. We're working on a high temperature thermoset with good lubricity when coated as a film and cured thermally. And when it does, chemical resistance-wise, because of the smoothness of the films that we're working on, the high hermetic sealing or barrier property between the carbon steel and the produced fluid, we have advantages over some of the epoxy and urethane systems that have been tried as internal coatings. Simply put it, one of the paradigms we'd like to use in any coating for production is basically super hydrophobic and super oleophobic. If we can achieve both, in a coating, then we can mitigate a lot of the scaling problems and deposition problems as well.
Excellent. All right. Well, as I said, that was the last question we would be taking here in the session. If you have any questions at all, my email address, gerald@parkafm.com, is in the main chat module, so you can email me there if you have any questions about park systems. If you have any questions for the professor, his email address is there on the slide currently being displayed at the bottom, rca41@case.edu. On behalf of the professor, Case Western Reserve University, and also Park Systems, we thank you once again for taking time out of your day to join us for this particular session. Be on the lookout for future invites to other Nanomaterials webinars that we'll be providing on a monthly basis to you guys. The topics will change from time to time, so hopefully you'll join us next time for our next topic, which will be announced very shortly. Thank you again, and that will do it for today. Any last words, Professor?
Well, thank you for joining us, and hope to hear from you or hear from me again.
All right. Okay, everybody. Thank you very much.